Okay, hi, I want to talk to you about series circuits today. And we were introduced to the concept of series circuits. It's just a circuit where all components are in a single path, right? And here's a series circuit right here that includes a battery, 1, 2, 3 resistors, and all the resistors are in a single path. There's also a series of equations that you'll find in the reference table pertaining to series circuits. There's a separate one for parallel circuits, and we'll do another video on that. And that just shows you relationships between current, voltage, and resistance. So it says, for example, the current, which is the current total, is equal to the current of through component 1, which is equal to the component through component 2, which is equal to the current through component 3, etc. It just is a fancy way of saying, hey, if you've got a certain number of amps leaving here, it's a series circuit, so that current has to flow through every part of it. And that current doesn't get diminished as it goes. We talked about conservation of current. So if you've got 10 amps that go through R1, you've got 10 amps that go through R2, you've got 10 amps that go through R3, and you get 10 amps back. So the total current of 10 amps equals the current of 10 amps through 1 equals 2 equals 3. Voltage, for example, I'll put a total here too. Voltage total is equal to V1 plus V2 plus V3. So this currently only has one battery, but imagine that I added a second. I'll just add a cell to it. And so if this was 9 volts and this was 3 volts, the total voltage we just add together, assuming that they're oriented in the right direction, which I neglected to do. I'm going to change this. That should be short and that should be long. Let's get the positives right up, because the positives, okay. So 9 volts plus 3 volts, your total voltage in this case would be 12 volts. If you add 3 9-volt batteries together in series, you'll end up with 27 volts. If you add 3 1.5-volt batteries together, you'll get 1.5 plus 1.5 plus 1.5 would be 4.5 volts. Pretty straightforward. Equivalent resistance. Now, we kind of need to understand what the term equivalent resistance means. And so, equivalent resistance is kind of a way of saying it's the total resistance of either the circuit or just at least a part of the circuit. So, but it is also kind of a way of saying it is the resistance that would be equivalent to adding another resistor to it. So imagine this is my circuit diagram. I'm going to get rid of that. We have R1, R2, and R3. So let's just say that they're all 10 ohms. So 10 ohm plus 10 ohm plus 10 ohm. We see the equivalent resistance is equal to just adding them up. And it kind of makes sense, right? The more resistance you have along each path, the less current is going to flow. Just imagine like rocks in a river, right? The more rocks you put in the river, the less current will flow, or the more resistance it will get when it flows. So we can add them up and say REQ is equal to 30 ohms. Now what that means is that's another way of saying that it is equivalent to a circuit like this that just had a single resistor that was 30 ohms. So this is equivalent to that. It's the total resistance of the circuit, but it's equivalent to another one that would be like this. I mean, it's also technically equivalent to you could have a 10 ohm and a 20 ohm resistor. This is equivalent resistance to this circuit. They both have 30 ohms of equivalent resistance. It would be like saying this REQ is equivalent to R2 plus R3. So R2 plus R3 is a total of 20. R1 is 10. And this is important to note because when we get to some of these hybrid circuits, you might want to play around with components. You kind of want to deconstruct it into something simple and then build it back up into something more complex, as we will see later on. I'm going to give you an example of a series circuit and how we can work through it. So let's take something like this right here. You can see there's an ammeter and 3 that measures 5 amps and 1, 2, 3 resistors. So we could find the total resistance, for example. We know the resistance for each of these resistors. It's 10, 20, and 20. REQ is just equal to The total, 10 plus 20 plus 20 is just 50. And we can use Ohm's law. This is what I put here. You can use Ohm's law, which is V equals IR, rewritten as R equals V over I. You can use this in circuits, and we will use it in circuits all over the place. Because you can use it for the whole circuit, or you can use it for any individual components of the circuit. So let's go back to this right here. So if your total resistance is 50 ohms, and your total current, because this measures the current through this, this, and this, is 5 amps, you want to find the voltage of this cell right here. V equals, if we take this equation, rewrite it, V equals IR. Current is 5 amps. Resistance is 50 ohms. So you get a total of 250 volts. Not big. So you know that your battery right here is supplying 250 volts. Let's say you wanted to find the voltage drop of these different components. They don't all have the same voltage drop. I'm going to go through that here. I'm going to erase this stuff in just a sec. So make sure you pause and write anything down if you haven't yet. We're going to work with Ohm's law. I'm going to leave this up here. So now let's just deal with R1, R2, and R3. I'm going to call that R1, R2, and R3. So that whole V equals IR thing works for R1, R2, and R3. So you can say if V equals IR, then R is voltage over current. And this should be true for the whole resistor, the whole circuit, but also true for each of these individual components. So if for the whole thing we know R is, let's just start with the whole thing. Let's just do R total, right? Is V, which is 250 volts, divided by 5 amps, divided 2, and you get 50 ohms, just like we said our equivalent was. So that's for the whole one, but let's do individual ones like R1. R1 is going to be V over I. So R1 is going to be, oh, we haven't figured that out yet. We need to do that. I'm doing this the wrong way. I gave you R1, R2, and R3. Okay. I need to find, I'm sorry, the voltage drop. So V equals IR right there. So let's go with R1. So V 1 is going to be current times R1. And we know the current through each of them is 5 amps. And the resistance of that is 10 ohms. So that gives us a voltage of 50 volts. So R1 is going to have 10 amps and 50 volts. Let's repeat this for V2, R2. So V2 also has 5 amps, but instead it has a resistance of 20 ohms. So the voltage should be 5 times 20 or 100 volts. And if you do this for R3, you'd find it's also 5 amps times 20 ohms or 100 volts. And if you want to confirm that you did this correctly, you can say, hey, what is V1 plus V2 plus V3? Add them together, you get 50 plus 100 plus 100 volts for all of them. I'll put a little V here, which adds up to a total of 250 volts. That should be your total voltage. And if we look, in fact, at the battery, we already figured out that it's 250 volts. And we see that V total is V1 plus V2 plus V3. So 250 equals 50 plus 100 plus 100. Looks good. It looks like we got this correct. So we have figured out not only what the total current and voltage and resistance is, we've also found the voltage, current, and resistance in each of these separate components. And you can do this in lots of different ways. We'll get practice a little bit on doing it in different ways. Like maybe I didn't give you a current, maybe I gave you a voltage instead. So you can be working in different directions, but you're going to use the same techniques of using V equals IR, Ohm's law, for individual components and for the whole battery. Oftentimes you're going to want to figure out the equivalent resistance before you do anything else. We'll get more practice on this, but I think this is enough for now. So I just want to say thank you very much for watching.